And I hope with this talk to shed a bit of light on some areas relating to the COVID pandemic where there's confusion and uncertainty. The difficulty with understanding an epidemic of any kind is that experts don't explain epidemiology clearly, and fake experts fill the gap, making it worse. So what I aim to do here is to explain the basics, and in particular to help you understand what drives spread. So the three factors in how a virus spreads when it first appears is how contagious it is, how long an infected person stays contagious, and how society mixes. Those three things combine together to give us a number called R0. This is called the basic reproduction number. It's the number of new infections for each infected person in the situation where everyone they encounter is still susceptible, in other words, has no immunity. So let's have a look now at what happens as infections spread. We get a new kind of R value, sometimes called plain R, but I prefer to call it RT because it's the value at a particular time. It's called the effective reproduction number. And it's the same thing as R0, but it now takes into account how much of the population is still susceptible. So if somebody who's infected meets someone who's now immune because they had the disease and recovered, or even somebody who's still infected, they can't pass it on. So as the disease spreads, you'd expect RT to gradually get smaller and smaller, whereas R0 is a basic property of the disease, and that shouldn't change. All right, so let's look at what the effect of containment measures is by working through these things one at a time. Well, first of all, let's start with how contagious the virus is. Well, for quite a while, that didn't change until the last quarter of 2020, when more contagious variants start to surface. And the thing with more contagious variants is they take over fast because they have a competitive advantage over the less contagious variants. So let's move on to the next point, which is how long an infected person is contagious. That has really not changed much because although we have medication to prevent the more serious form of the disease, we don't actually have any effective antiviral drugs. The best medications we have so far treat the symptoms and make them less serious. So let's look at the next point, which is how society mixes. Well, R0 varies depending on how much mixing there is in society. An average value that was mentioned early on was 2.5, but it can be a lot higher than that in a society that mixes a lot, and lower in a society where, for instance, people live low density or don't use mass transit. So this, though, gives us the basis for non-pharmaceutical interventions, or NPIs, masking, distancing, hygiene, ventilation, and so on, because the idea is to fake the effect of a less contagious disease. So this draws on the idea that R0 is lower in societies that mix less. So if you can fake the effect of a society that mixes less, that will slow the spread. So let's now look at what happens as the disease is progressing and the issue of how much of the population is still susceptible. So the first effect is immunity after being infected, and so far there's been quite a low rate of reinfection, so the immunity, if you actually catch the disease and recover, seems to hold up reasonably well, and that's a good thing. Vaccination would stop it a lot faster because you can vaccinate a large fraction of the population relatively quickly once the bugs are worked out of the system. And of course, new variants can add in complications. They may possibly defeat the immunity either from a previous infection or from a vaccination, which could mean that we have to have more than one round of vaccination. But we'll deal with that when we get to it. So finally, back to what we can do to contain the spread. And as I said before, until such time as we can deal with the disease more directly through vaccination, or ideally more effective treatments, even antivirals, NPIs are the main game, and they mostly address mixing. It's very important to understand, though, about this is that if we relax these measures, we stop faking a less contagious disease, which means that it springs back. So this is why I don't like the idea of calling it waves. It makes it sound as if it's a disease like flu that comes back seasonally after having gone around the world. But in fact, it's still in our society and hasn't gone away, unless we happen to be lucky enough to live in a country like New Zealand that has effectively suppressed it. So it's really all one wave. We only partially suppress it, and then it comes back when we ease off the suppression measures. So I found a nice simplified epidemiology model. The web page it's at is at the bottom of the slide, and can play around with the parameters on that to change the rate of spread. And first I'll run it without interruption, and then look at how we can make it do something that looks like waves by suppression measures and relaxing the suppression, and then going through a few cycles of that. So first, there's the simulation, and before I run it, just to explain a few things, the top left panel allows me to change how fast the disease spreads. So the simplest one to change is the average number of days between infections by one individual. If you set that to 4, and you assume that you go from being infectious to recovered in 10 days, then that would give you an R0 value of 2.5. And the other things that the simulation will show is the number of fraction of the population exposed. That means they're infected but not just infectious. And there will be a dashed line illustrating the herd immunity level. This will take about 30 seconds to run, so let's let it go, and I'll explain as we go, and then when it ends. So first of all, the number of infections is rising quite slowly, and now they're starting to take off increasingly steeply, and when the pink curve intersects the vertical line, it starts to go down. The horizontal line is the herd immunity level, so 60% of the population has been infected and recovered at that point. And the important thing to note is that the number of infections drops fairly quickly from that point, but a lot more than 60% are infected at the end. So the herd immunity level is not the end point. And so we end up with nearly 90% of the population being infected at the end. You look at the lower half of the panel on the left, you'll see R0 is still 2.5 because we haven't changed the disease. But R, or which I prefer to call RT, is now 0.26. So if there are localized outbreaks, it doesn't spread very far, because as soon as R is below 1, the number of new cases does not accelerate. So herd immunity starts when R or RT is equal to 1, and it can only go down from there unless you make it easier for the disease to spread. In other words, if you do something like increasing the amount of mixing in society, or it gets more contagious. So this model assumes the disease does not change and the society does not change. So it is simplified, but does give you some idea. So overshoot makes herd immunity bad. As a strategy, some people say, oh, just let everyone get infected and herd immunity will take care of it. But with such a high rate of transmission, almost everyone eventually would get infected. And with the more contagious variants, where R0 is probably quite a lot above 2.5, be close to 100% of the population before it actually stopped. Vaccines are a much better way to achieve herd immunity, because if 60%, or whatever the required level, is immune already before an outbreak, it doesn't spread very far. So you get rid of that overshoot problem. So let's have a look now at an example where I look at the effect of making interventions. And to keep it simple, I'll assume each time the intervention is perfect and instantaneous. So if I change the rate of reinfecting from 1 every 4 days to a longer number of days, then you immediately start seeing a dip in the number of new cases. So the thing to watch when I run this until I make an intervention, R0 stays on 2.5. But because my interventions will fake the effect of a less contagious disease, it doesn't matter too much what they are, whether it's lockdowns, masking or distancing, R0 on this simulation will actually drop. And then if we relax the interventions, then R0 will go up again because we are now reducing the effect of faking a less contagious disease. So let's let this one run now. And as before, at the beginning, the number of cases grows quite slowly. Watch for the pink area of the curve to start growing. And this time around, before those numbers get too large, we'll introduce an intervention where we slow down the rate of transmission. So instead of once every 4 days, we set it to, say, once every 20 days, which you might achieve with a lockdown or very extreme social distancing measures, and let it run again. And now you'll notice it peaks quite quickly. In real life, not quite so good because we don't implement these measures quite so perfectly. But then numbers start dropping, and we get to a point where we think, oh, it's not so bad, we'll relax the measures. Not quite back to where it was before. We've now got a bit of distancing, etc., so it behaves as R0 is 2, the actual R value is 1.7, so that's above 1, so it's going to start accelerating again. So we hit a point again where we make an intervention, and not quite as severe as the first case, so maybe not a lockdown and just curfews or other such measures. Number of cases starts dropping again, and we've now faked a disease where R0 is 0.83, actual R value is 0.67. So we relax a bit again, and note that we've now gone back to a version of containment where R0 would be 2, and so it takes off again, and we again put in some containment, numbers start dropping again, and we're now faking a disease where R0 is only 0.83, but remember, we're faking that. If we got rid of all the measures, R0 would go back up to 2.5, the current R value would be a lot higher than 0.59, so it could take off again. So look at the wavy sort of nature of this. The disease has never gone away, we've just suppressed it and then relaxed the suppression measures. But note, at the end of this year of doing this with the disease, 70% of the population is still susceptible, as opposed to letting it run wild where only 10% would still be susceptible. There's still a lot of space for it to take off again. If in fact we got rid of all containment measures, we would still reach herd immunity when 60% were infected, but we wouldn't overshoot as much because of the immunity that is already in the population. So waves, no. The surges and peaks are a result of NPIs and then relaxing them. So we might get tired of distancing, masking and so on, but COVID doesn't. And we really need to avoid big outbreaks because they make new variants more likely. The more of the virus there is out there, the more chance it has to mutate in many different directions, and as soon as one of those directions is more contagious, it's going to become the dominant variant. Just to finish off a few other myths, it's not seasonal. South Africa had peaks in summer and winter last year. The simulation I ran was not based on our dates, so you wouldn't have seen it then, but July, December, January were really bad months, so it's not a winter or summer thing. There's no miracle cure. The televangelist medics first started hydroxychloroquine and then ivermectin, but there's no evidence that they are effective, certainly nowhere near effective enough to make a big difference. Also, finally, it's not only the elderly. Young people are much less likely to get it badly, but new variants can change them. So be careful, people. In summary, vaccines are frustratingly slow, and we may need some reruns if new variants surface. So understand the epidemiology. Only then will containment and the apparent waves make sense. So I hope I've shed some light on that.